Hello and welcome back to our series on genetics. We are in part 5 where we are looking at a special type of trait called a sex-linked trait. Now, most humans have 23 pairs of chromosomes. That gives us 46 total, 23 pairs. Most of your traits, your hair color, your eye color, your height, all those things that make you you are going to be found on the first 22 chromosomes. These are called autosomal traits because they are found on the chromosomes called autosomes. And autosomes are special chromosomes that are carrying your normal everyday thing. So I guess they're normal chromosomes, your autosomes. But you have a 23rd pair called your sex chromosomes. That determines whether you will be a male or a female. And in humans, that comes in X and Y chromosomes. And as I said, they determine your sex. Generally, XX is female, XY is male. Although if you get into some genetic diseases, that differs a little bit, such as if you only have a single X chromosome, or if you have two X chromosomes and a Y, it differs a little bit. But generally, XX will give you female, XY will give you male. But they don't just determine whether you are a male or a female. They do carry some inheritable traits on them. And if a trait is found on that chromosome, the sex of the child will affect its phenotype. Such as with color blindness. Red-green color blindness is found on the X chromosome. And hemophilia, your ability to clot your blood and stop bleeding. People with hemophilia have trouble with that and bleed very easily and have trouble stopping the bleeding. Both of those traits are found on the X chromosome. And so for both of those traits, the sex of the child will affect its probability of receiving it. So I guess it doesn't really affect its phenotype. It affects the phenotype and the probability of having the disease. It affects both of those. So there are three different things that we use to talk about these people. First, someone of the normal phenotype and genotype, because for this, phenotype and genotype, you don't really have a heterozygous that's the same as homozygous dominant. Normal would be no trace of the disease, and that would be all of your chromosomes, all of your sex chromosomes, do not have an affected gene. All of the genes that you received on your sex chromosomes are normal when regarding that trait. All of those would be normal. You can also get a thing called a carrier. You don't have the disease, but one of your X chromosomes is affected. One of them has a normal gene, one of them is affected and has a gene that codes for the disease. However, most, if not all, sex-linked traits are recessive. So if you have one normal and one disease alleles, the normal will cover it up and you will not have that trait. However, you can pass it on to your child. And if you have not yet figured out, since you need two X chromosomes to cover it up, almost every single time it is only possible in females. In fact, it would be only every single time, because if you were to be an XXY male, those two X's would be pretty much clones of each other. So it's really only possible in females because you need two X's to cover it up. But unfortunately, sometimes all the chromosomes you get have the allele for the disease. And those people are affected. They have the disease. So normal would be no trace of disease. For like color blindness, it'd be myself. I do not have color blindness. I am not colorblind. Affected would be my Uncle Gary. He was red-green colorblind. The X that he received from his mother had the red-green colorblind allele on it. And being a male, he only received that one X. Therefore, he couldn't be a carrier. He was affected by it. But his daughter, Melinda, is a carrier. She is not colorblind, but she received a colorblind allele from her father and a normal allele from her mother. Therefore, she cannot have it. But any children that she would have, she is able to pass on that colorblind gene to her children. So that is a sum up of sex-linked traits. Let's look at how it would affect a Punnett square. So for this, we're going to choose, we'll say, color blindness. Color blindness is an affected trait. So for this, we're going to choose, we'll do just a regular C. So for this, if you have nothing, and it's color blindness is only found on the X. Am I able to? I'm not able to write up there. Color blindness only found on the X. If it is a normal X, then it is the normal allele, regular color seeing. However, if it is an X with a little c above, it is the colorblind allele. So for this, we will say that we'll look at, for example, my uncle and my cousin. You get my uncle. Uncle Gary. He was colorblind. He was also a male. And you get his wife, named Denise, who was not colorblind and was not a carrier. So first thing we need to do is look at, we need to make males and females. We need to see what the kids could be. And we do that just like any other Punnett square. You have two chromosomes. You have X chromosome. You have a Y chromosome. And for Denise, who was female, you get X chromosome and X chromosome. Now, you move this one as normal to there, and down here, and the Y. Whoops. There, and there. All right. And for Denise's chromosomes, X as well as X, and X as well as X. So the same thing that you would be doing with a normal Punnett square. You just move them over. You will also find that it tells you that to get a boy or a girl is a 50-50 chance. 50% of the kids you're going to make are girls, and 50% of the kids you're going to make will be boys. However, now we need to look at the alleles that we are given. Denise is normal. However, Gary is colorblind, so we need to put that C on his X. All his X's will have the colorblind on them. So we need to go back and put little C's onto those X's. That means we will have a carrier female, a normal male, a carrier female, and a normal male. So the chances of having a colorblind son are 0%. So colorblind son, 0%. You cannot have a colorblind son. So both of the males that you make will be normal. Both of the females that you make will be carrier. So all of your daughters will be carriers. Now, what if we look at this, such as we will label one of these M for Melinda. This would be my cousin, who is a carrier. Let's look at her and her husband. So, we move that over here. Again, X equals normal, XC equals colorblind. So we move those again. Match those up. Now looking at it, you will have colorblind son, carrier daughter, normal son, and normal daughter. Let's go ahead and move that normal up here, or that carrier. So here you'll see is where it really starts to matter what sex you are. Because if you are a female, which would be these two, you have a 0% chance of being colorblind as a girl. However, if you are a boy, which would be the top, you have a 50% chance of being colorblind. And that is why sex-linked traits are different than the other traits. It depends on whether you are a male or a female. It affects your probability of getting the disease. It is much, much, much more common to find sex-linked traits on males than it is on females. So our next video that we are going to do, and most likely going to end our look at genetics, will be what do we do if we are tracking two different traits? For example, what if you're tracking blood type? You have the normal A blood type, B blood type, AB blood type, and O blood type. That's one trait. However, if you want to track your true blood type, you also need positive and negative. That is a completely different second allele. If you want to track both of those, you need a Punnett square that will be able to track both of those. And for that, it would look very similar to this. However, instead of 4 squares, you will have 16 squares in your Punnett square. It sounds difficult. It is not. We will look at that in our next video.